Hi, welcome back. On today's lecture series, we are going to discuss about unit commitment. So here we have to do the empathy. So we have to feel that the problem first. What is the problem that arises? So in the operator side, a grid operator faces 20 generators, which one to start up for tomorrow's load curve. So that's for the prediction. Okay, an operator is faces 20 generator, which one to start up for tomorrow's load curve. So we don't know among 20 which one has to be turned on and which one has to be turned off. It is a large confusion to the operator. And the cost to pay. Running too many units of generator, it wasting the fuel. Running too few risk blackouts. So every wrong decision cost lakhs of rupees. So this is a main issue. If you are without knowing this, if you are turning on the number of generator, the large amount of fuel, the large amount of the rupees is gets wasted. And the time constraint. If generators cannot start instantly. The thermal unit need hours to warm up, and planning must happen 24 to 168 hours ahead. So what exactly unit commitment? So the unit commitment is the problem of determining the what is the optimal schedule, which generator has to be turned on and which generator has to be turned off, and which one has to be keep running. So our planning horizon to meet the load demand at minimum total cost. So we have to decide which one has to be turned on and which one has to be turned off. It is based on in order to attain the objective of the minimum fuel cost as well as startup cost as well as shutdown cost. So Harjan, we have to take at least and typically 1 week. So why not just run all units? It is nothing but in spinning losses. Ideal units consume fuel even at no load. So unnecessary unit inflate operating cost significantly and the wear and tear. So in thermal cycling damage, turbine blades each startup as a finite cost modeled explicitly. So if you go for several years, the wear and tear cost is also very high. And the minimum up down times. So the unit must stay on or stay off for a minimum period. So as a hot typical constraint, it is based on the load forecasting and the spinning reserve. So committed units must provide enough headroom to handle sudden load increase or generated trips. So the key constraint has to be involved in the unit commitment. That is nothing but and power balance. So here the sum of committed, the total generation from all the units which is committed, which is equal to system load plus the losses and the spinning reserve. So the total available capacity of on units which is greater than load, because here we have to ensure the spinning reserve, it should be from around typically 10 to 15% of total demand. And minimum uptime. Once started, a unit must remain on for at least some hours. This is to ensure the economical scheduling. And minimum downtime. Once shut down, a unit must remain off for at least some hours. And crew constraint. Limited operator may restrict simulations startup across the units. So the cost function. So this is to mainly minimize the total cost function. That is nothing but in fuel cost with respect to the quadratic equation and hot start cost and cold start cost and shutdown cost. Everything has to be calculated. So before proceeding. So here the solution method, we have to go with the priority list method. So rank unit by average cost. That is, it will be simple, fast one and suboptimal. And if you go for the dynamic programming, you have to do the dynamic programming over hours of the stage by stage, optimal but exponentially state space. And we have to do Lagrangian relaxation. So it relax coupling constraint near optimal scalable to large one and branch and bound. So interior programming, it will be exactly used in modern EMS softwares. So in the priority list method, we have to calculate the average cost, and based on that we have to ranking and we have to commit to meet the load demand and check the minimum and maximum up and down constraint, and we have to do the computing, we have to do the compute the cost. So in the dynamic programming for unit commitment, it is based on the state grid, transition arrow, goal path, and node cost, etc. So the main one, the state transition cost and regression equations. And for an example, you are having the three units, unit 1, unit 2, unit 3. So the minimum and the maximum generation from the particular unit 150 to 300, 600, 100 to 400, 50 to 200, like that. And for the cost equation, that is nothing but fuel cost equation is given, and hot start off and the cold down, everything is given. Okay, also the power demand and what is the reserve capacity, everything is given. So based on the priority list, we have to do the assign the which unit has to be turned on and which one is has to be turned out. So these are the few real-time applications which are used in the NLDC, National and Regional Load Dispatch Center, and we have to integrate with the renewable energy integration like solar, wind, etc. And also it can be interfaced with the EMF and the SCADA systems. So this is a mind map for why unit commitment, what are the constraints we have to be followed, and what is the solution method, and what is the cost model. So this is an accurate challenge. So the EV person, if 10 lakh EV plus in at 9 p.m., how does unit commitment respond in real time? What new constraint appear? If you know the answer, just to put in the comment section. And another question. A system has 4 thermal unit, you have to do the priority list method of the loaded 3 requires 3 units. Unit 2 has been off on only 1 hour, but the minimum downtime is 3 hours. It can be committed at 3 hours. You can justify the answer. So these are the few references for this topic. Thank you.